computational decarbonization, which is actually the reason I'm here, because we have a project meeting tomorrow also with Priya, and it's a very exciting project thinking about how you can use computing for decarbonization and how we can decarbonize computing. Okay. So what is a carbon sensitive electric load? Well, so first, let's just acknowledge that electricity generation produces carbon emissions. And as the electric grid is transitioning to incorporating more and more renewable energy renewable sources of generation, these emissions are becoming increasingly time and location varied, meaning that if you use electricity during a period where there's a high shares of wind generation and solar generation, you can plausibly say that the carbon emissions associated with your energy use is going to be lower. So this sort of gives an opportunity for carbon-sensitive electric loads to adapt their energy consumption to try to use electricity when it's low carbon rather than when it's high carbon, and thereby try to help reduce emissions. So the question that we've been interested in trying to answer here is then related to defining this carbon footprint of electricity consumption. And in particular, what I, as a consumer, can do if I want to contribute to a greener grid in real time. So like, what can I do today to try to help lower grid emissions? And so I think that for people who work in electric power systems, there's sort of been this general idea that, you know, the way to do this is really to help the grid, to participate in programs like demand response, to do peak shaving, try to avoid having to ramp up natural gas generation, or maybe more actively participate in the market, which after all, there's some correlation between the price of electricity and its carbon intensity, particularly because low carbon resources like renewable energy are technically zero marginal cost. And so that's sort of, I think, been a lot of the narrative, at least in the electric power systems, is sort of, let's help the grid function more efficiently. Let's enable sort of a longer term integration of more renewable energy. And that is going to help generally reduce carbon emissions. And I'm just going to say that I'm still a believer that this is maybe the right way to go. But it turns out that the rest of the world, who doesn't really like think about electric power systems all the time, for them, it's a little like roundabout way of getting at this problem. This seems, it's very hard to quantify the exact carbon emissions impact of, for example, demand response participation or actions you might take in a market. And so it turns out that from sort of a consumer perspective, it is much more appealing to sort of this idea of more directly aiming to use electricity when it is low carbon. And so one example of this is if you look at the iPhone, it has a clean energy charging by default. And so there's been a number of such efforts. For example, I mean, one example from Apple using sort of creating this easy to follow signals that are supposed to help an iPhone and other devices understand when the electricity is greener, so you can use electricity then and charge then rather than during high carbon times. Examples from Samsung, who does sort of automation of electric devices for end users to try to help run them and skew their electricity use to times of low carbon emissions. And of course, we have large companies like, for example, Google, who's been looking at shifting data center loads also with a goal of trying to reduce emissions. And one of my favorite examples here is from the National Grid in the UK, who has this product, which I call the green light signal. This is a light bulb you can buy and connect with an app, and it will light green when the electric grid has a lot of green energy. And so just to say, like, this is not sort of not happening, this is already ongoing. And so what is motivating our investigation here is not necessarily that we think this is the way carbon sensitive loads should interact with the grid, but it is already happening and it's a trend we need to understand.
So just a question.
Yeah.
So this UK example is very nice, carbon intensity.
Yeah.
But if you go to, let's say, New England site, it also shows the carbon intensity.
Right.
So is it the same carbon intensity as they show in UK, the way of computing, or different in the US? When
I I can't tell you exactly. There are multiple competing definitions of this carbon intensity, and I'll get to that in a little bit because that is part of, that's an important part here. I will also just say that as these things came out, I mean, I know that Samsung uses data from electricity maps, which is generally looking at average carbon emissions in the grid. I don't exactly know what Apple uses. It's been hard to understand that. But yeah, there are, at least when I was trying to look into this, I wasn't able to find out. And I think also the National Grid, I'm not sure if they are also using average carbon.
So there's no definition which is well established.
Well, there are some that are more well established, but it's not necessarily that they are necessarily the best. So yeah.
So maybe you'll get to this, but on the one hand, traditionally you would want loads consumers to respond to the conditions in the grid and the prices, basically price responsive demand. But now we want to respond to carbon emissions as well. So are those signals aligned typically, or would they put in different directions?
Yeah, so that's a great question. So yes, of course, traditionally, price responsive demand has been kind of what we've been hoping to see, and maybe we haven't seen as much. And I think this is kind of interesting because this is actually consumers want to know the carbon intensity of electricity so they can respond. So clearly this is incentivizing people to take action. The question of how does this align with price signals? So there is some correlation. Again, there's oftentimes like the cheapest resources that are often renewables, which are very low carbon. But it's not 100%. And so when you start looking at this data, you see that it's not a one-to-one correlation. There are also so there's maybe a general correlation, but then there's also times at which it's like really not aligned at all. This has to do with things like you might have different, more carbon intense resources sort of replace each other.
Yeah.
We'll get also to some more of this. So yeah, so essentially, just some examples of carbon sensitive electric loads. So essentially, the definition here is that carbon sensitive electric loads are electricity consumers ranging from individuals to companies to organizations that are interested in reducing the carbon footprint of their electricity consumption. And so many people would like to do this voluntarily to help mitigate climate change. I think one good example of that is individual consumers oftentimes have fairly flat electricity tariffs. And so you have some wiggle room in which you can adapt your electricity use without actually increasing the cost like what you have to pay for electricity. And then we have carbon reporting requirements or carbon reporting willingness. An example of that is hyperscale computing companies that often want to publicly demonstrate a commitment to clean energy. And so this type of carbon reporting typically rely on things like the greenhouse gas protocol in order to demonstrate and compute their carbon emissions. In addition to this, there's been a recent shift towards also, for example, in clean hydrogen production, there are electric loads whose profits and revenues rely on the greenness of the electricity that they are using. So for example, when we're looking at clean hydrogen productions, there's been production tax credits that have been outlined where how much you are getting as a production tax credit is really strongly correlated with the carbon emissions of the electricity that goes into the electrolyzer that produces this hydrogen. And so you can see that in this scheme here, you can see that there's a really strong incentive to achieve very low carbon emissions, which means that you need to demonstrate that you have access to really low carbon electricity. And so this is an example from the US. What will happen to these production tax credits is a question, but there's also similar things happening, for example, in Europe, where you have renewable fuels regulations that also define green hydrogen. And so this kind of puts a lot of money behind this question of what qualifies as green electricity.
Yep. Is that hourly accounting or yearly average accounting?
So the greenhouse gas protocol. I think under the greenhouse gas protocol, you can use yearly accounting. In the European regulations on this, there is currently monthly requirements. Also in the intended, the intention here has also been to transit, like both in the European regulations and the US regulations, has been to more and more move towards like hourly accounting, so more time matching. What I will be describing here is more related to the time matching question. So, okay, But so now we know that people care about the carbon footprint of electricity. But the question really is, like, as you said, like, what is the carbon footprint of electricity really? How can we define that? And so if you think about this, you kind of know what the emissions from generation are. Like, there are, okay, there's some like uncertainty there about exactly how we calculate those, but generally speaking, we can say they are fairly well defined. I can also quite well define the total grid emissions because I can calculate those from the emissions from the generators. Of course, again, there are things I have to account for, like exports and imports and so on. But generally speaking, there are established methodologies for calculating the total grid emissions. That still begs the question, how should we define the emissions of individual consumers? Because individual consumers are drawing electricity from a grid that relies on a mix of generation resources. And once those resources put the electricity into the grid, it's kind of mixes, right? And we don't really know, it's hard to say exactly what electricity ends up with what consumer. Did you have a question?
Yeah, I'm wondering, so this is a lot based on marginal emission, it seems like. But I'm wondering, what do you do with say I build a hydropower plant in Brazil, and now I'm slowly decomposing all the organic matter, regardless of whether or not I'm producing electricity, the methane is just going into the atmosphere. But if I hadn't built that power plant, I wouldn't have the carbon emission. That methane emission. So.
Yeah, so I don't think I am going to get to the question of like beyond, I mean, like what happens when you build a new power plant and that leads to emissions, for example, during construction or during operation that are not directly associated with the electricity. This is not only about marginal emissions, so I'll talk a little bit about that. But yeah, maybe I don't think I'm going to get really to that, but I'm very happy to discuss it more. Okay. So this is hard to define. That is one thing I just want to say. There is no way of sort of directly tracing electricity, or there are methods to trace electricity from source to sink, but those are not unambiguous. There are different methods for doing so. And even if you could trace physically where the electricity is flowing, it doesn't necessarily account for the way, electricity markets do dispatching, and therefore like kind of defining what is the contribution of any individual load to the emissions that come from the overall grid. Okay, so this is hard, is the first thing I want to say. There are many different ways of doing so, but of course we have ways of still trying to define this. And in particular, sort of the main way in which people do carbon footprint accounting for electricity consumption is as laid out in the Greenhouse Gas Protocol, which has a Scope 2 emissions accounting guidance. And so there are two main methods for doing emissions accounting. One of them is market-based accounting, which is based on things like renewable energy certificates or energy attribute certificates and power purchase agreements. So these are essentially financial contracts that you have with a renewable power plant. And so again, here there's tightening restrictions on where you can get these from, like currently you can get them from like kind of anywhere, but there's increasingly restrictions that you should get in the region where you're actually consuming electricity. And then there's the other way of doing this is location-based carbon accounting, where you are looking at carbon emissions directly from the grid where you're consuming electricity. And I'll just say that the fact that we have these two methods create a lot of challenges. There's a potential for double counting of renewables. So for example, when we're doing location-based carbon accounting, if you're in a grid where there's a lot of renewables, there is no one who can tell you whether or not the renewables in that grid were already essentially under power purchase agreements. And so someone might be already counting them towards their accounting, but then it might be counted for everyone else as well. So there's challenges like that. And I should also say that many of these challenges are acknowledged. I mean, also this, as we discussed, sort of the increasing temporal and regional granularity of where these market-based accounting schemes should be allowed to be sourced. These are all kind of parts of kind of ongoing updates to the Greenhouse Gas Protocol. So a little bit of what we have also been wanting to do here is to both understand this landscape, but also help inform that debate. Yeah.
Maybe like a silly question, but so with double counting, is it also that there's like triple counting, quadruple counting in these accounting schemes? Or is it just like, is a kind of potentially like dumb solution to be like, everyone should like purchase renewables at double their consumption? Like it basically is it in principle solvable via a really simple hack, or is there actually like something more nuanced going on where you really could have like quadruple counting in something and has to be fundamentally fixed?
I think that one of the so that's a really good question. I think that some of the challenges here is that, like, for example, say I am a consumer of electricity and I have a power purchase agreement with a power plant that is in a different region, then I am going to technically count the energy produced by that plant towards my own consumption and claim that I am green, even if the grid I'm in is not. And then the people in that grid is also going to claim that they are green because they consume that energy. And so that's a kind of a double counting. But there's a lot of nuances there also where, like, maybe I am have a power purchase agreement in the same region where I'm at. And so I'm kind of, there's
Really
only a partial double
double counting,
counting. There's also things where, people are like, you can do combinations of those. So you have like market-based carbon accounting plus some residual accounting, like that accounts for everything you haven't taken care of. And so I think there's a multitude of like different ways in which, so I don't think it's a simple solution you could make. And also you should say like, okay, so yeah, even if you knew all of this and tried to somehow take it into account here, I don't think it's very clear how you would do that, but maybe, yeah. Mm-hmm.
I think the greenhouse gas protocol is mostly meant for businesses and organizations, right? So there's also maybe a mismatch between, let's say, the scope of the organization and then the whole region.
Right. Yeah. So that's another question, right? I mean, like how the fact that the companies are, able to buy all of this and count it towards their carbon accounting. I mean, I think one good example of this is in in our home country, me and Audun's home country, Norway. You had all the hydrogen producers were selling RECs to German utilities, and the German utilities claim we are all green. And then the Norwegian consumers obviously knew that they are only consuming hydropower, but in fact, they should have been consuming, the coal power. And so, so there's a lot of like kind of how you perceive and what really happens here. I don't know if I actually really answered that question, but yeah. Okay, good. So what I will be focusing on is this question of location-based carbon accounting. This is partially because it's just, I think there's a lot of scope for understanding that better. That's where we can contribute maybe as like more technical grid people. And I will also just highlight that in these regulations that are being laid out on clean hydrogen production, there has been explicit like questions about how do we demonstrate zero or minimal induced grid emissions through modeling or other evidence, and are there ways in which we can do that, and if so, how should that be done? So in terms of location-based carbon accounting, the current standard for this is to use just average carbon emissions. And I would say that probably if you look at anyone who just talks about carbon intensity of the grid, the majority of times they are going to talk about average carbon emissions, which are just defined as the total carbon emissions in the grid divided by total energy use. And so the benefits of using this as a metric is that it is fairly easy to compute and widely available. So for example, this is a map taken from electricity maps that shows carbon intensity across a range of different regions. This is from January 8th this year. And essentially, this can be used also, this average carbon emissions is sort of acknowledged as a way of doing accounting under the greenhouse gas protocol. So that is kind of, where we start.
Average in time there, or
the time involved in this?
Yeah, so what's the time frequency or resolution?
So you can, under the greenhouse gas protocol, do yearly average carbon emissions. But you can also do more like temporally granular hour by hour. And so, for example, electricity maps, who releases a lot of this data, they are sort of suggesting that they think it's better if you use, so they have hourly data available, and they, would suggest that that is maybe what you should be using. And I think, so that's kind of where we're moving towards also with this, all of this is kind of moving towards greater temporal and spatial granularity, which I think is very good because that's how the grid is functioning, right?
Sorry, one more question.
Yeah. Mm-hmm.
Is this ratio conditioned on the local pricing structures and other kind of location-specific consumer behavior?
So this is only looking at the total carbon emissions from generation in a region.
So is it like to be understood at a regional level?
Yeah, so it's like, for example, I don't know, so if I look at the US, right, you can see that there is kind of the different ISOs have different are defined as different regions with different carbon intensities. So you have like CAISO, you have PJM, these
But
different
these
regions. I
were
just
not
have one
controlled
number.
by- Regions which are not controlled by markets. It is the same definition.
Yes,
Okay.
yeah, I would say so. So there's like, you have the markets in the US, you have the markets in Europe, which are zonal. I don't know exactly how the market in India works, but there's another, but you can also see that, so there's an intention here to make it as like spatially granular as possible. But you have, I mean, there are, yeah. So essentially here, the way this is computed is just by looking at the grid emissions from generation and then dividing by the total electricity use. They have, I mean, Electricity Maps, who has developed this data, they've also done a lot of modeling in terms of trying to understand imports and exports, because in many tightly coupled grids, it's really important to know, you know, I don't know, California is importing a lot of hydropower from the Pacific Northwest, for example. Okay, so that's how this is computed. And then, I mean, if you think about it, I think most of us like are, you know, people who like numbers and signals, and that gives us an opportunity to take action and improve things, right? So the first thing that is logical if you have this data is to just count your emissions and say, okay, how bad is it? But then the second step is, of course, to try to take action to reduce your emissions. And that's the question that we were like, what happens when people are trying to use this data to reduce the emissions that are being assigned to them? And essentially, that is kind of getting at trying to answer the question of whether average carbon emissions is an effective signal for helping loads to become green. And so that's, I'm going to show you a little case study on that. And so that brings us into this question of carbon-aware load shifting. And so the example that I'm going to bring here is based on the example of hyperscale data centers. And so this is just, you know, based against the backdrop of the current investments in massive new power-hungry data centers. We also know that many tech companies have made commitments to use green energy, and we know that there is an interest in that industry to try to see if there is possibility to adapt power use to reduce emissions. So essentially, the idea here is that we are working with something like what you see here. We have an electric grid in black, and then we have a network of data centers that is modeled on top of that grid. So this network of data centers have an opportunity to shift computing workloads between locations and also in time. And by defining kind of different shifting capacities and shifting costs, knowing about maximum computing capacity, and sort of trying to model this network of data centers, we can then, you know, model data centers' capabilities for doing temporal load shifting, meaning starting, stopping, or resuming jobs, and geographical load shifting, where you're working on like load balancing between different regions. Of course, when you're doing this kind of shifting, there's a lot of limitations you have to take into account, like latency, data availability, hardware requirements. Essentially, you wouldn't want to, you don't want to compromise performance too much. But at the same time, so there's a lot of things to take into account here, and I'm just going to tell you that we are not accounting for anything of this in the models that we have at the current point. But this is things you are working on, you know, improving and understanding better. And so the kind of basic thing that I think is important to know here is that algorithms for workload scheduling and load balancing, they already exist. And so the question is, you know, can you plug into them to try to make them more carbon aware? And if you look into sort of the literature on this in the computer science domain and computing systems, there's been an increasing interest in doing exactly making these scheduling algorithms carbon aware. And so the question that we are trying to answer here is less, is this possible? It is more, what happens if this vision is realized? Okay, and so how are we going to analyze this? So we will look at a setting in which we are considering a system operator of the power grid, which clears a day ahead electricity markets, thinking about it like 24 hours across time. Then we will use the output of that electricity market to compute carbon emission data. And then we will provide that carbon emission data to the data centers to allow them to optimize their load shifting with the goal of reducing emissions.
That is the only objective?
You can also balance it with cost, for example. But yeah, that's sort of what we're looking at here. we are not, I mean, there's a lot of things that you can look at cost of electricity, and you can also look at, of course, cost of shifting in that problem. So essentially, the market clearing is modeled just using a simple DC optimal power flow where we are minimizing hourly cost. And then we are leveraging, as I said, the output of this problem. In this case, first, we will look at average carbon emissions. We'll get to other definitions later. As I said, total carbon emissions divided by total electricity use. And then we will solve this optimization problem where we're assuming that the data center operators themselves are trying to minimize emissions by shifting in load, computing workloads in time and space. And so in particular here, we are only having an objective where we're looking at only minimizing carbon emissions, but you could extend that easily to also have additional terms accounting for cost and both of shifting and of power. So we looked at formulations like that as well. So very simple here setup. I will just highlight that when we are computing average carbon emissions, we are getting one value for the whole grid. We are looking at shifting within one grid here. So we are actually not really, when we're thinking about carbon emissions, average carbon emissions, it's a little bit less important to shifting in space. We are allowing for it here, but just to kind of highlight that.
What is then the subscript I on lambda?
That would be the shift. So I represents different data centers.
So, but you said that the lambda is homogeneous across all data centers.
So for average carbon emissions, yes, it would be. I'll show an example later where we're looking at marginal carbon emissions and locational marginal carbon emissions where the lambda would be different across space.
So, so this is not a hierarchical model. It is two different models, isn't it?
Yes, it is not a hierarchical model. So we've also explored this question in terms of bi-level modeling. We looked at the version where we were kind of where we had the a data center in an upper level problem, allowing the data center to adapt its load to try to minimize emissions in the grid. And there's also been in literature other people who've looked at sort of letting the data, like the ISO, sort of know about how loads would react to carbon emissions data, and then having an upper and a lower level problem like that. So those are options. And we're also currently exploring sort of equilibrium modeling for this problem to try and understand these different setups. The reason I'm showing you this here is because it is maybe the most practical example of what would happen sort of right now. And because it's completely sequential, doing this requires zero changes to the electricity market. And so it's essentially trying to model what loads are already doing. Okay, so this is
So here the assumption is that if you're doing the space-time load shifting, you are assuming that when data centers are not serving some load, it is going staying idle during that time.
So we are assuming that in the data center, there needs to be some headroom available to allow for shifting, meaning that if you're shifting away from a data center, yes, you would likely have idle time on the servers, and that is, I mean, currently also, if you talk to computing companies about this, tech companies about this, they will generally say, we're happy to be flexible, but don't touch the compute. We'll build you a really big battery, but don't touch the compute. We'll build diesel generators, whatever, but don't touch the compute. And so I'd say that some of this is a little aspirational. It's not clear that it is sort of something they would implement tomorrow, but there is an interest in doing this and moving in this direction, and who knows where we are actually moving with all of this. Maybe we will have periods of overcapacity, and maybe this will become more important.
Yep. I'm curious, would there be any way to kind of monetize that value of the reduced utilization rate of the server and then kind of penalize that in the function?
I think there could be, and yes, I mean, so we've been trying to find collaborators and people to work with on understanding those aspects as well. And I think that's a really kind of important next step for this type of work, is to, with data centers in particular, is trying to understand what does this problem actually look like? Because it's just one thing, it's definitely not exactly like this. Yeah. Another question?
Yeah, maybe similar to Rob's question. So you do the dispatch, and then the data centers react to the carbon emission signal. But that may then they
What
may
happens
have,
next?
I mean, they may create an imbalance, or they may need to create balance payments and so, right?
Perfect, thank you. I'm just going to continue my presentation because we'll get to that. All right, so thank you. That was a great segue into this slide. So essentially the idea here is that we are looking at market clearing day ahead, and then there's of course going to be a real time or an intraday market as well. And so essentially the new data center load profiles become an input to that intraday market. And in this case, the system operator will clear the intraday electricity market. We can compute carbon emission data. And then, of course, after that, we can compute the data center emissions as well. And so we've done, I'll show, there's other ways you could do this. You could have this happen, this be a real-time market and, sequentially rolling it forward. That makes it a little harder to think about time shifting. So for right now, we're just kind of thinking about this. We've done the other case as well, and I'll show some brief results about that later. So why do we use this setup? Well, so this setup allows us to assess, first of all, the estimated reduction in emissions as the data centers think that they are, what are the emissions reductions that they can achieve when they are doing that optimization problem. So this is just essentially the outcome of the data center optimization problem. Second, it allows us to look at the actual reduction in assigned grid emissions. So, when I get this carbon emission data, I can now take that data and again compute data center emissions. And so there can be a discrepancy here because when the electricity market clears and I get new carbon emission data, this data might be different from that data, right? So you're going to consider both sort of the estimated reduction that the data center thinks they can achieve and then the actual assigned emissions. And then, of course, we're also interested in just understanding the total system emissions that arise from these electricity market clearings and understanding, does this actually impact grid emissions in a positive way?
So can a data center node free ride on other data center nodes in terms of maintaining their operation, but not actually reducing the emissions? It could happen at...
yeah, so they could. Yeah, we will see that a little bit. So do you mean within the data center, or do you mean?
No, so there are two
overall
different
grid?
data center nodes, right?
Mhm.
And if I try to, so I can act locally such that I can actually have some externality on the other data center node.
Yeah, that's also, yeah. So that's definitely. So this is also, I should highlight this, that, here we are assuming that the data center load profiles are the only things that change. And and that is, an unrealistic assumption. In a real market, there would be more other changes that would happen. There could be more other loads that do this. And definitely there can be, you could probably be very strategic about like what you're doing here and then try to impact the sort of carbon emission data at another data center location, but without doing anything. So yes, there's an opportunity, I think, for that as well. You all have very good questions. That's great. Thank you. Yeah. So what does this case study that we are setting up? So we are looking at this data center load shifting. We're using this simple small test system, the RTS-GMLC test system. It has 1 year of hourly data. It's quite renewable heavy. So you can see that, the yellow parts here are the nodes, gray lines are the power lines. And then you see all these like green and brown dots. They are the different, these are the different carbon emission intensities of the different generators. Okay, so lots of renewables and then both coal and natural gas. So we are assuming that we have 4 data centers in the system. So they are located at these red circled nodes. Each of those have about 250 megawatts of average consumption. And this equals approximately 20% of total system load, let's say. Data center loads, 20% of total system load. And so that is kind of fairly comparable with the amount of power consumption that we're seeing from data centers in regions like Virginia or Ireland. They all have about 20% of load from being consumed by data centers. So as I said, we allow the data centers to do spatial and temporal load shifting by choosing where and when to process workloads. And we are assuming here, for simplicity, that this allows for an increase or a decrease of consumption of up to 50 megawatts at each location. And so essentially what this tells you is that we are allowed to shift about 4% of the system load around by shifting at the data centers.
So is there a sorry.
Oh.
Go ahead.
What's your assumption on the load profile of the data centers?
So our baseline assumption is that it's flat.
Okay.
Yeah.
And
So
is there background load?
there is background load. Yeah. Of
And
course.
what assumption on that?
So we are assuming, so we have 1 euro hourly load data. So this system was developed, I think about like 5-6 years ago to represent like the year of 2020 with renewable generation and load data in these regions. And so there is a time varying load and there's time varying renewable energy generation in the system. And so that is like everything that is grayed out now. And then we're just like kind of dumping the data centers into that system. Yeah.
I guess one more question is, do you have any and I think someone from the chat also asked it a while ago, which is, do you have any assumption on the cost of shifting load temporally or spatially?
So we don't have that integrated here directly. So we haven't made any assumptions. I mean, in what I am presenting right here, right now, we do have, and I'll talk about that in a little bit, like sort of a version of this where we were implementing also a quadratic cost of shifting. What that number should be, we didn't, I mean, we varied it and we looked at it, but to do an analysis. But of course, that would be like one of these important changes that you'd want to do to the model to ensure that you get that well represented. Okay, great. Okay, so again, what we're going to do here is that we're just going to first count the emissions from the data centers, and then we're going to second try to shift the load to minimize emissions, and then assess what happens. And okay, this is taking long. I'm taking very long here, but I'll try and wrap this up so you get some things here with you. So the data center load shifting, when we first do the counting of emissions, we see that data centers are across this full year, data centers are assigned about 3 million tons of CO2 emissions, which account for approximately 19% of system emissions. So they have like roughly the same percent of emissions as they have of the consumption. So that's sort of where we start. Then after we do the shifting to minimize emissions, we get an expected reduction in emissions of about 6%. And so so that is what happens here. But then the shifts in consumption are large enough to, again, shift the generation mix and thereby also impacting the average carbon emissions. So when we look at the assigned emissions after the shifting, it turns out that we only decreased emissions by about 3.7%. Okay, so expected emissions were larger than the assigned ones, but generally this is also still a kind of decent reduction in emissions overall. So at some level it's working. So we could say, okay, does this look pretty good? The one thing I haven't told you anything about here yet is how what happens with the overall system emissions. And so that comes next. And so the unfortunate fact here is that if I compare the emissions, the total system emissions before shifting and after shifting, it turns out that shifting by the data center, although it reduced the assigned emissions to the data center, actually ended up increasing total system emissions by 0.3%. And so essentially what is happening here is that data centers become cleaner while all the other loads in the system become dirtier.
Can you explain a little bit more?
Yeah.
Can you explain a little bit more? Yeah.
I mean, should I explain? Yeah, so essentially, the data centers are taking actions to try to shift their load into periods where the grid is cleaner, and they seem to achieve that. But somehow the changes in the generation dispatch leads to an increase in emissions overall. And so this is headline numbers for a full year. So I'll maybe get to like a little bit more of the details on what is going on here in a moment. But let me just say here that like kind of the conclusion that we find here from this specific, of course, this is system specific. If you change the data that you're working with, it could look different. But this is data, this is not things we invented specifically for this purpose. This is really kind of just a standard test case in power systems. So there's no reason to believe that this couldn't happen in reality. And so the really sad conclusion here is that even if the data center really believed that they contributed to lower emissions and they were assigned fewer emissions, their action actually increased emissions. And I think sort of the really like sort of broad strokes thing here is that we can say that average carbon emissions just doesn't tell us anything about how a change in load will change emissions. And I'm also just going to say that I think this is problematic if this is the metric that consumers are optimizing for under the greenhouse gas protocol.
So I know there's discussion around average versus marginal emissions. So
I'm coming to that in a second. So let me maybe so next slide.
This is all planned, right?
So yeah, for those of us who are used to thinking about that, I think it's pretty clear that average carbon emission tells you something about the full stack of generators. It doesn't tell you anything about like what's happening on the margin. So why not use marginal emissions? So locational marginal emissions are defined as a change in carbon emissions given a change in electricity use at a given location. And so essentially this metric, of course, much more sort of detailed describes the emission impact from a change in load, meaning how a marginal generator moves. I'm just going to say there are versions of locational, like marginal carbon emissions defined slightly differently than how I will define it. And the way I will define it is based sort of on how we define LMPs. And I think that in sort of US, particularly in US electricity markets, this makes a lot of sense. So essentially, this definition of locational marginal emissions, I think, seem very logical to us also because it feels very similar to locational marginal prices. But I think it's important here to just also be aware that whereas LMPs are related to the cost minimization objective of the OPF itself, and can be derived, by looking at dual variables of the solution to that problem, locational marginal emissions have to be calculated using a slightly more involved sensitivity analysis of the OPF solutions. And I'm not going to go through that in too much detail. We have a paper that describes how that is done, but essentially you're doing sort of standard linear programming and sensitivity analysis here that allow you to define how the optimal generation dispatch would change as a function of a change in load. And once you know how the optimal generation dispatch would change, you can look at how the change in emissions would be. And so that is sort of the next question then is that, sure, let's say this is the metric you're using, how does that impact what does that mean for our load shifting? So essentially, we do exactly the same thing as we did before, except now this metric is going to be spatially resolved. So we have a different value for each node, which also means that it's more interesting to do spatial load shifting. But otherwise the sort of process is the same. Okay, so what does that look like? So if you first go through the step of counting emissions, we observe that data centers are now assigned 6.6 million tons of CO2, which is again 20% of the total assigned system emissions. When we do our shifting of load, we see that the data centers in their shifting objective find that they can reduce emissions by 4%. In reality, I mean, since this locational marginal emissions is sort of a sensitivity value, it is more sensitive to shifts that happen due to changes in the generation mix. And so actually, if I look at the post-shift emission data, it turns out that the shifts that happen with the data centers only reduced emissions by 0.9%. So essentially, one takeaway you could take here is that emissions reduction now look lower than before. And our prediction here is a little overly optimistic. So this was a bit more overly optimistic than it was before. And so you could imagine that if a data center is allowed to choose, should I use locational marginal emissions or should I use the average carbon emissions? In this case, I'm able to get smaller emission reductions with my load shifting. However, if any of you look closely, you would notice that the scale here is different. So here I'm looking at almost 6.7 million tons of CO2 emissions that were assigned. And previously, I only had 3 million. So average carbon emissions gave me much lower numbers. And so what happens there? Well, so just to say, this is looking at just the data that gives us the assigned system emissions. So if I assign emissions based on locational marginal values, I get a total system emissions that is almost twice as large as the actual system emissions. And this is because the locational marginal emissions only tells us about what's happening on the margin. It does not tell us anything about the emissions of the generators that are not on the margin. And so as a result, we can assign too many emissions or too few emissions, and it all comes down to how polluting is the marginal generator in the system. And I think that this is kind of an important difference from LMPs. So when we are looking at locational marginal prices, we know that we will always choose to first dispatch the cheaper generator, and then the latest generator to serve a node is going to be the most expensive one. And so the LMPs kind of sort of tells us about the marginal cost of the marginal generator, but it also tells us something about the cost of the other generators that were dispatched before that. With emissions, there's just like no such relationship at all with the marginal emissions. And so still, it is interesting to look at the total emissions here. So what we saw is that the data centers were able to decrease their emissions when they did shifting based on locational marginal emissions. And it turns out that when we're looking at the total system emissions in this case, those emission reductions hold up. So in this case, the data center shifting did reduce total system emissions, and in fact also contributed to a reduction in emissions from the other loads. So sort of from the system perspective, this is a much more effective way of contributing to total system emissions. And in a way, that's not super surprising because this metric is essentially setting out to tell us when is it most effective to scale back consumption. Okay, so this was all yearly data. Here are some results for daily shifting. So in here, this is daily reductions in carbon emissions. So changing carbon emissions is on the x-axis. This is a histogram that just shows the number of occurrences throughout the year. And essentially at the top here, we're showing the graph for shifting with locational marginal emissions. Here's with average carbon emissions. And so what you can see is that essentially 0 here indicates that there was no change. If I'm at the negative side, it means I reduced emissions. If I'm at the positive side, it means that I increased emissions. And so what you can see is that for individual days, I mean, both of these methods can lead to either increases or reductions in emissions, but we see that in general, the shifting with locational marginal emissions has a tendency to provide reductions in carbon emissions, whereas average carbon emissions, unfortunately, many times can lead to increases in emissions. So that is sort of what we see here. These are just the quantiles that are marked in black. Okay, so if locational marginal emissions are better, why don't we just use them? Well, so one challenge here is that verified data is only available in very specific regions. To my knowledge, only in PJM, though this is developing very rapidly. So this carbon data is thankfully becoming more available. And here I'm talking about locational marginal emissions at sort of the scale of electricity market clearing. Also, as you can tell from this picture, this is actual PJM data. Locational marginal emissions are very unstable, which can make them very hard to predict and act on. And as we discussed, it's a little hard to justify using locational marginal emissions for accounting since total emissions can just be so widely different from the total generator emissions. And I realized that we are like really at the top of the hour. So if anyone, I don't know if I'm allowed to continue for a little bit more, but if anyone needs to.
Maybe 5 more minutes, but we also have some questions in the chat.
Okay. So I'll wrap it up in less than 5 minutes. So essentially, one question we can ask here is whether we need new metrics. So we have locational average carbon emissions, and we have adjusted locational marginal carbon emissions, which are 2 alternative metrics that we've been looking at. Locational average carbon emissions essentially is based on something called carbon flow, and they seek to trace carbon from source to sink using what is called the proportional sharing principle at each node. So that's a specific choice made there. And they essentially, one nice thing about this way of assigning emissions is that it ensures that the assignment of carbon emissions is consistent with sort of physical power flows, and total emissions assigned to loads is equal to the total emissions from generation. However, they do not have that like kind of marginal aspect to them. We also tried a different new metric that we proposed, which is adjusted locational marginal emissions. And here the idea is just that you use the locational marginal emissions, but you adjust them by a constant shift factor just to make sure, just to align such that total emissions that are assigned across all loads is equal to the total emissions from generation. And so the nice thing about this metric is that it maintains similar differences in carbon intensity across locational marginal carbon emissions in a given time step. So this means that actually if we are doing geographical load shifting and not looking at shifting in time, then this would actually give the same result as the LMCE. And then also it becomes, LMC here is the locational marginal emissions, and it becomes similar to average carbon when there is no congestion in the system. Unfortunately, when we're looking at both spatial and temporal emissions, what we found, these are histograms similar to the ones I showed before. The baseline here is on average, we don't see any change in emissions at all. So that's a little disappointing. Okay, so there are other, as I said, there are other setups in which you can use in order to evaluate this. You can look at more real-time market clearings. So we've looked at that. And essentially similar results from that, where we see that locational marginal emissions is the most effective signal for load shifting. We see here, and also in other parts of our work, that it's important to try to keep individual shifts small and build up over time to avoid overshifting. And this is kind of where you use something like a regularization parameter that can also be interpreted as a quadratic shifting cost. And so that is kind of how far we have gotten with like the shifting cost itself. But it kind of helps in many ways to assign a shifting cost in terms of accuracy as well. Okay, so that's sort of the shifting here. So what I would say is that, I mean, there are questions, maybe we can come up with better metrics for this and so on, but there are some fundamental limitations to what load shifting can achieve. So carbon sensitive loads can only change how, when or how much they use electricity. And that means that they can only impact that marginal generator. They cannot change the order in which generators are dispatched, which is still only based on cost. And so there are ways in which you can try and fix this. So the right approach, you could say, is maybe to add a tax or a penalty on generator emissions. And that has the effect of making low carbon generators more cost competitive and potentially bringing them further down in the merit order. It can be politically challenges because it requires agreement on a carbon price, or it can also make electricity more expensive and thereby also reducing the demand. And I know there's been analysis of the European markets when this has been implemented, which has shown that the reduction in demand actually probably had a larger impact on carbon emissions than this changing of the merit order of the generators. We recently started thinking about maybe a different approach here, where you could allow sort of two-dimensional consumer bids, where you would allow consumers to submit not only bids for electricity consumption, but also define sort of essentially a carbon-dependent utility of using electricity. So saying that if the electricity is more carbon intensive, then I value it less. And then we proposed a way of kind of trying to change the market design to maximize social welfare under consideration of the carbon side consumer cost. And so there's a paper there, a preprint. This is very new. I had a couple of slides on it, but I'll just sort of skip over that. Essentially, the core thing here is that you're introducing this sort of carbon-independent consumer utility into our problem, along with some a method for doing carbon allocation. Okay, so I'll probably end there. I mean, what I've been trying to tell you is that carbon-sensitive loads, I think, might become an increasingly important group of loads in the future. I think there's a potential that they could really help reduce emissions. But if that should be possible, we have to have a system for carbon accounting that is fair, transparent, and aligned with the physical operation of the system. And in particular, it has to reward actions that truly reduce total carbon emissions and not only shifts emissions to other loads. As we also I've tried to explain here, is that carbon-based load shifting has limitations. And therefore, I think it's also important that we kind of explore other ways and maybe more productive ways for consumers to express their carbon preferences within electricity markets. Okay, so I'll end there. We'll have a software package if anyone wants to try it.
chat.
Yeah.
There are some questions in the
Open the
in
chat.
section.
Sure. Yeah, of course, yeah.
But I don't want to go before the.
Let's wait for a few minutes for the chat part because you can also read it here.
Oh, I can also read it there. Okay, I have it here now. Yeah, so I took a talk about shifting cost. And then, okay, so there's several questions about sort of the questions of like cost of shifting on the data center side and also like potential latency implications. I think this is extremely important to understand better in order to understand the potential here. There can be, so I don't have any detailed sort of currently I don't have like very good ways of saying how we would model that. But definitely, you would imagine that a system like where you are shifting between data centers, of course, would have to account for all of those kind of latency and costs associated with shifting, both energy costs. You can imagine that the hardware might have different efficiencies, and therefore you would also impact how much energy used. There might be losses in shifting, and so I think there's a lot of opportunity for improving that optimization problem and model that more accurately. Yeah, and I think that someone is also asking about whether if the kind of power consumption remains the same after load shifting, whether that implies that the overall computing performance remain unaffected. It doesn't, I mean, again, I'm just going to give the very unsatisfying answer of probably not. This is probably not an accurate enough model to represent how this actually would impact computing performance. And the key question here is really what amount of shifting and what amount of flexibility could you possibly get from a data center without significantly impacting computing performance. And I think there are, you can look into that literature and look at what companies are doing, and there are opportunities for managing workloads without significant hits to performance, but finding out what type of workloads that is and how much flexibility, I think remains an open question and an important direction for research as well. Yeah, I think that is maybe, and there's a question about whether there are I take this question as asking, so is the renewable dispatch limited by congestion? Is there any system characteristics you've seen which lead to more or less accurate LME for system response prediction? And so we haven't analyzed in detail how much the LME changes before and after shifting. And definitely, I think that this will be very system dependent and also depend on congestion. So of course, we looked into that a little bit, but in particular, if I think that this is also what we see when we are looking at these impacts from day to day, is that different load profiles with different forms of congestion will impact the effectiveness of this data center shifting problem. And so clearly there's an important aspect of the underlying system conditions on how well this works. Sorry, that was trying to answer a lot of questions online. Yeah, you have a question, I think,
Yeah, I was wondering about your assumptions on the baseline about the capacity mix and like how the actual capacity mix of the system affects us. Like, is this a very coal intensive generation mix we're looking at? Is it natural gas intensive? Like, whatever you. Yeah.
Right. So in the system that we are looking at here, it is not a very, there's a lot of renewables in the system, actually. So that is also, I think, part of like when we're seeing these big variations in what happens in the system across the year, it has a lot to do with the fact that there are varying levels of renewable generation, varying amounts of load. One thing here to note is that the coal power plants in the system, if I remember correctly, yes. We actually had an issue where we had some issue in our data where we had flipped some carbon emission data for the coal and natural gas power plants. And so if you do that, you get very different results. Yeah. But in this system, the coal power plants are less expensive than the natural gas power plants. And that means that they are coming earlier in the merit order. And that means also that it kind of breaks this assumption that like increasing cost is going to lead to increasing emissions as well. And so if you do that flip between the natural gas and coal power plant emissions, you can see there's a stronger alignment between price and emissions, and that then would change some of these.
That's what I was wondering.
results
So
as
like
well.
in systems where like coal is going to be, you know, basically removed from the system, or like they're going to be removing that from the system. Like what does that mean? So in a natural gas peaker.
Yeah, in a
situation,
natural gas. Yeah, so this is kind of a natural gas peaker system, I
Right.
would say.
Yeah.
And then I think, yeah, so like how does as the generation mix evolves? I mean, definitely there are questions you could ask there. I'll just say also that like when we're looking at, for example, the PJM data, we've been doing some analysis on like the correlation between price, like LMPs and LMCs there. And there are, you know, they are correlated, but there are some like really big mismatches as well. So but yeah, clearly, I mean, so the analysis that is here is not meant to say like, oh, this will be like this everywhere. Important caveat to put in there. I think that one thing that is important to know here is that I mean, this is kind of more trying to demonstrate that this can happen, and we need to be aware of that. That it's not always very well aligned, the signals we are using with the actual emissions reductions.
Okay, let's stick around for it. So can we have the question after the lunch perhaps, or?
I just want to ask one
Okay, go ahead.
question. So you mentioned the carbon price or tax as an option. Did you try to simulate that in this case?
In this case, so we have not simulated impacts of carbon taxes in this system specifically as of right now. And so I think it's an excellent suggestion to do that, in the exact same study.